Thank you for introduction, Chairman. So I'm Yuta Naruse from Chuo University in Japan. So I make a presentation. This is outline. The introduction. In a factory, there are numerous pipes, and they are used for transporting fluids, and they are narrow, complex with many bends and long distance. But they sometimes have corrosion and cracks due to aging. So inspection is required to maintain the quality of transport fluids. So pushing endoscope is existing inspection methods. This is inspection by a worker manually pushing an endoscope into the pipes. But friction caused by deflection. Pushing force is not transmitted deeply. So self-propelled endoscope, that is inspection robot, is required. So these are existing robots. Wheel robot is difficult to minimize, so unsuitable for narrow pipes. Interim robot is lack of traction. Traction means force to pull wires, so unsuitable for long distance pipes. As1 robot is lack of propulsion. Propulsion is forced to go deeper into the piping, so unsuitable for complex pipes. So we need compact, high traction, and high propulsion self-propelled inspection robot. So this is a previous story. We developed pipe inspection robot Pyro. This is compact and flexible structure with high output. This is driven by air pressure and has gripping unit and extension unit. Figure 1 is that operation. So we experimented that robot in the factory. So figure 9 is the course of experiment and result. Point B is objective point, but the robot stopped at point C. When the stopping robot has traction load about traction load 131.8 Newton. So, but a robot has 150 Newton in theoretical value. So robot stopped because the traction force became less than the traction load. So my research object is inspection of narrow, complex, and long pipes. Conditions under which the entire conduit can be inspired is pulling force larger than traction load. So to solve the this object, I have two methods. Method 1 is increased traction. This is increased drive pressure or in cross-sectional area. But this has problem. That is pressure resistance and space limitation in piping. So method 2 is reduction of traction load. This is few examples of research and room for dignity. So I try this. In this page, I talk about traction load. Cause of traction load is friction between wiring and inner wall of piping. And especially traction load happens in curved pipe. For example, figure 12. An increased traction load due to increased inspection distance and curved pipe. So we need to reduce friction and tension. So these are existing traction load reduction methods. Braided strip is decreased coefficient of friction, but that is lack of traction load reduction. Capsule decreased reaction force, but gets stuck in the pipes. Connected multiple robot is decreased tension, but limited space pipes makes it difficult to assemble. So new traction load reduction methods are needed. So I focus on pipe inspection gauge, PIG. PIG is used for cleaning inside pipes, and PIG is made by silicon. So PIG, when the PIG attached to the wires with the robot, so if we push the PIG, we can reduce the tension. So, but we have problem that is constant friction and load and difficult to pull out. So we developed a variable diameter tension release system, TRM. So this is a load reduction mechanism to increase the inspection distance of the robot. By making the outer diameter variable, that can reduce the traction force required for robot movement and can be pulled out after inspection. Before TRM expansion, TRM has no friction, but after TRM expansion, we can push the TRM. So I talk about this. So this is a operation of TRM. I talk about the details next slide. So first, when the robot stops, air pressure applies to TRM. And next, push TRM by air pressure. So the robot can move. Next, decrease air pressure of TRM and pull back TRM and repeat thereafter. So that cause capable of distributing the source of force in a narrow tube, and increase in inspection distance can be expected with standalone. So this is a structural variable diameter TRM. TRM is has two flanges, and two flanges are connected by artificial muscle and latex tube. Latex tube TRM has a chamber between artificial muscle and latex tube. Figure 23 is motion of the TRM of expansion. This is the FBD of the TRM. So we obtain the push force by the one. Artificial muscle may dent when external pressure is higher than the relationship between internal and external pressure of TRM. So that causes the cross section and pressure decrease. So I confirmed by the experiment. So this is a experiment. Figure 26 is the environment. In the stainless steel pipe, the expanded TRM is pushed by the air pressure. The result is the figure 27. So in this figure shows the gap between theoretical and measured value. Difference from the theoretical values occurs as the indentational pressure increases. So this is a picture. Figure 28 is in this experiment. So when the pushing pressure is larger than the TRM internal pressure, the TRM dents air pressure and air leakage occurs, resulting in pressure loss. So we operate with pushing pressure less than internal pressure. So this is the conclusion. A summary is trial manufacture of variable diameter TRM as a method for reducing traction load on robots. The variable outer diameter TRM was tested and confirmed to generate pushing force of 40 Newton. Future work is there improved TRM withstand pressure and conduct other characteristic tests, wiring pushing test while mounted on a robot. Thank you for your attention.
That's an important problem industrially to clean long pipes. Are there any questions to the speaker? Okay. I have one. How long have you achieved so far? How many meters length of pipe can you go down? Yes.
Yes. In the previous study, this robot can move about 50 meters, but we required more than 20 meters. So this
Okay. Quite good. Any more questions? Anyone? Okay, thanks very much for important talk. Thank you.
Thank you.